Most commonly, the flux of any component is down the composition gradient. If Ji represents the molar flux of component I and dxi by dz is the mole fraction gradient, Ji divided by the negative of the mole fraction gradient is positive. Downhill diffusion equalizes compositions, occurs spontaneously, it increases randomness, and downhill diffusion produces entropy. The focus of this presentation is on uphill diffusion, and the molar flux of component I divided by the negative of the mole fraction gradient is less than 0. Uphill diffusion of any component consumes entropy. For binary mixtures, uphill transport is only possible if the Fick diffusivity of that component I is negative, or if we use a pump to transport that component uphill, as is done in reverse osmosis. Uphill diffusion may occur during transient approach to equilibrium. Here's a picture taken in Antarctica showing fortresses of ice containing nearly pure H2O in contact with seawater that contains salt. The question arises why there is no diffusion of salt from seawater into the ice fortresses. In order to resolve the paradox observed in Antarctica, let us resort to the Gibbsian thermodynamics of phase equilibrium. For two phases that are in thermodynamic equilibrium, the chemical potential of any component must be equal in either phase. The chemical potential of any component is written as the chemical potential in some standard state plus R times T times ln of the activity, where the activity is the activity coefficient times the mole fraction. The chemical potential is the partial molar Gibbs free energy, where the Gibbs free energy has two contributions, the enthalpic contribution and the entropic contribution. These represent respectively the unmixing and the mixing tendencies when the system is subject to perturbations in composition. S is the entropy and is given by the Boltzmann equation. S is K ln W that is engraved on his tombstone in Vienna. The symbol W stands for Wahrscheinlichkeit. You will note that Josiah Willard Gibbs and Ludwig Boltzmann were contemporaries. The red line shown here is a plot of the Gibbs free energy for the ice crystals, plotted as a function of the mole fraction of sodium chloride. The blue line is the Gibbs free energy of seawater plotted against the mole fraction of sodium chloride. The seawater contains significantly higher concentrations of sodium chloride. The phase equilibrium between the ice fortresses and seawater is described by the common tangent between the two curves. And this tangent intercepts the x1 equal to 0 axis at this point, which represents the chemical potential of water in the ice that is also equal to the chemical potential of H2O in seawater. At the other end, the common tangent intersects the x1 equal to 1 axis, at which the chemical potential of NaCl in ice is equal to the chemical potential of NaCl in seawater. What we note is that there is equilibrium between the ice fortresses and seawater, but this equilibrium corresponds to significant differences in the salt concentration in the ice fortress and in seawater. This example underscores the fact that the mole fraction differences or mole fraction gradients are not the proper driving forces for molecular diffusion. Let us examine a set of experiments conducted in 1949 by L.S. Darkin. The experiments were carried out with 2 bars of steel that are brought into contact with each other. On the left side, we have the composition of 0.48% carbon, 3.8% silicon, and the remainder iron. The right hand side, the bar contains 0.45% carbon, practically the same as in the left bar. Significantly lower amount of silicon, 0.05%, and the remainder iron. The 2 bars are raised to a temperature of 1323 Kelvin by placing them in a furnace for 13 days, and thereafter the bars are quenched and the compositions of carbon along the distance from the interface measured on both sides. We note that the diffusion profile or the concentration profile for carbon exhibits a minimum, and then it increases near the surface and then decreases to the value that is equal to the initial value. So in this region, the carbon atoms experience uphill diffusion from a low concentration of carbon to a high concentration of carbon. This is a technique used for surface hardening because the surface now contains a higher portion of carbon and is harder than the bulk that is tougher. So carburization using this technique involves exploitation of the principle of uphill diffusion. Let us examine the darkened experiments in a little bit more detail. The addition of silicon to the left compartment or the left bar increases the escaping tendency of carbon and therefore influences the activity. The activity of carbon in the mixture of carbon, silicon, and iron is a function of both the weight percent silicon and the weight percent carbon. For a given weight percent carbon, the addition of silicon increases the activity of carbon. If we replot the experimental data in terms of the activity against the distance from the weld interface, we note that the activity progresses monotonously from a high activity region to a low activity region and does not show any minimum or maximum. In other words, the experience of uphill diffusion is not observed when we use activity gradients as driving forces for transfer of carbon from one compartment to the other. On the basis of his experiments, Lawrence Stamper-Darkin drew the following set of conclusions that also serve as takeaways for this presentation. Firstly, the driving force in an isothermal diffusion process may be regarded as the gradient of the chemical potential. For a system with more than two components, it is no longer necessarily true that a given element tends to diffuse toward a region of lower concentration even within a single phase region. The word single phase is quite important, as we shall see later. The departure from the behavior of an ideal solution may be so great that the concentration gradient and the chemical potential gradient or activity gradient may be of different sign, thus giving rise to uphill diffusion. In proceeding further with our analysis of uphill diffusion, we draw inspiration from the works of four pioneers in the field of diffusion, starting with Adolf Fick, whose paper published in 1855 set out the Fick's law of diffusion, in which the flux is written as being proportional to the concentration gradient. The focus of Fick's work was on binary liquid mixtures. James Clerk Maxwell and Maxwell-Stefan focus their attention on mixtures of ideal gases containing three or more components. Lars Onsager, who won the Nobel Prize in 1968, wrote a seminal paper in 1945 where he wrote, "The theory of liquid diffusion is relatively undeveloped. It is a striking symptom of the common ignorance in this field that not one of the phenomenological schemes which are fit to describe the general case of diffusion is widely known. For an n-component mixture using matrix notation, the Onsager formulation for diffusion can be written as a column matrix of diffusion fluxes is proportional to the column matrix of chemical potential gradients, and the proportionality constant is a n-1 times n-1 square matrix L, and the elements Lij is equals Lji is the assertion that is termed the Onsager reciprocal relationships, or ORR. In our approach to formulating diffusion, we combine the approaches of Maxwell and Stefan by extending their formulation of diffusion in multi-component gaseous mixtures by incorporating non-idealities and introducing the chemical potential gradients. Let's begin by analyzing diffusion in binary mixtures of components 1 and 2. Let U1 and U2 represent the velocities of motion of components 1 and 2 in a laboratory fixed reference frame. U is the molar average mixture velocity. Since the chemical potential gradients are constrained by the Gibbs-Duhem relationships, only one of the chemical potential gradients is independent. The mole fractions sum to unity, and therefore there is only one independent measure of composition. In the Maxwell-Stefan formulation, the force acting per mole of species 1 is balanced by friction species 1 experiences in undergoing relative motion with respect to species 2. The frictional term must be proportional to the composition, and we take that proportionality to be represented by the mole fraction of component 2. The physical significance of the Maxwell-Stefan diffusivity, where we use the symbol D with a line through it, is that it represents an inverse drag coefficient. The force acting per mole of species 1 is a negative of the gradient of the chemical potential with the units newtons per mole. The Maxwell-Stefan equation can be reformulated in terms of the diffusion flux, which is defined as the flux with respect to the molar average reference velocity Vm is the molar volume of the mixture. Rather than use the chemical potential gradient as a driving force, it is convenient to define a thermodynamic correction factor given by this expression, which quantifies departure from ideality. Indeed, if the activity coefficient is unity, gamma is equal to unity. And the Maxwell-Stefan equations can be recast into the form flux of component 1 is proportional to the mole fraction gradient of component 1, and the constant of proportionality is the Maxwell-Stefan diffusivity times gamma. Therefore, in comparison with the Fick's law, we note that the Fick diffusivity equals the Maxwell-Stefan diffusivity times a correction factor that quantifies departures from thermodynamic idealities. Let us examine diffusion in the binary mixture of methanol and normal hexane at a temperature of 313 Kelvin. The Fick diffusivity is plotted here as a function of mole fraction of methanol. We note that the Fick diffusivity decreases by about an order of magnitude as a composition of 0.5 is approached from either end. By dividing the Fick diffusivity by the thermodynamic correction factor gamma, we obtain the Maxwell-Stefan diffusivity, and that Maxwell-Stefan diffusivity is practically independent of composition. This is the persuasive advantage of using the Maxwell-Stefan formulation, because it shows a more predictable composition dependence than does the Fick diffusivity. Now let's try and understand this reduction in the Fick diffusivity value as shown by the experimental data. The mixture of methanol and hexane undergoes phase splitting at temperatures below about 308 Kelvin. The green line represents the binodal curve, which is defined by the minimum in the Gibbs free energy, say at 290. These are the 2 points here where the partial derivative of G with respect to the composition x1 is 0. Those are the points. So plotting the minima in the Gibbs free energy versus composition curves, we can construct the binodal curve. The red line represents a spinodal curve. These are points at which the thermodynamic correction factor is 0. This is the same as stating that the second derivative of G with respect to the mole fraction is 0. So those are the points representing the spinodal curve. Within the region, the mixture will undergo phase splitting. Say if we take a composition here of 0.5, subject to a small perturbation, the mixture will yield a hexane-rich phase and a methanol-rich phase. The area between the spinodal curve and the binodal curve is a metastable region. A different way of expressing the phase splitting phenomena is to say that the Fick diffusivity is negative in this region. Now, the sharp decrease in the Fick diffusivity is due to the fact that at this temperature 313, we are very close to the two-phase region. Now, the phase splitting in liquid mixtures occurs too quickly or too fast in order for us to follow the diffusion trajectories. Diffusion in metallic systems occurs slow enough for us to monitor the composition trajectories that are followed during phase splitting. In order to demonstrate that, let us consider the binary mixture of iron and chromium using the thermodynamic data on the free energies, binding sex, and entropy of iron chromium mixtures. We can construct the phase diagram shown here. For all temperatures below 1100 Kelvin, the system splits into two phases. The green line shows the binodal curve, and the red line shows the spinodal curve. Along the spinodal curve, the thermodynamic correction factor is 0. And for the region indicated in gray, the thermodynamic correction factor is negative. It also suggests that the Fick diffusivity is negative in this region. That would lead to uphill diffusion. In this graph, the activity of each of the components, iron and chromium, are plotted against the atom fraction of iron. It's interesting to note that for iron, the activity gradient of iron is opposite in sign to the atom fraction gradient of iron. The same is true for chromium. The activity gradient of chromium is opposite in sign to the atom fraction gradient of chromium. Let us take a composition of 0.5 in this region and subject it to a small perturbation. Following up from the previous slide, let us take a system consisting of iron chromium at a composition of 0.5 in the unstable region. I draw only the chromium atoms here. Initially, the compositions are uniform in two regions, say within the unstable region. We subject the system to a small perturbation which leads to a higher amount of chromium in the left compartment than in the right compartment. Since the Fick diffusivity is negative in this region, this leads to a situation where the diffusion will be up the atom fraction gradient of chromium, and this would lead to an exacerbation of the segregation phenomena, with more chromium atoms migrating from the right compartment to the left compartment. So this is a self-accelerating process where uphill diffusion will increase the segregation of chromium in the left compartment and lead to a excess in the atom fraction of iron in the right compartment. It is useful at this stage to follow a simulation of this phenomena where we see that the segregation producing islands of chromium form within a matrix of iron that is indicated in red. We now consider diffusion in ternary gas mixtures, and the objective is to demonstrate the possibility of uphill diffusion in such systems. We begin by formulating the Maxwell-Stefan equations to describe the diffusion in ternary gas mixtures. The force exerted per mole of species 1 is balanced by the friction species 1 experiences because of relative motion with respect to species 2 and relative motion with respect to species 3. Similarly, the force acting per mole of species 2 is balanced by the friction species 2 experiences in moving relative to species 1 and the friction it experiences with species 3 in view of the velocity differences between species 2 and species 3. In view of the Gibbs-Duhem constraint, only two of the driving forces are independent, and there are only two equations to consider. There are three independent Maxwell-Stefan diffusibilities, D12, D13, and D23. These represent respectively the inverse of the drag between 1 and 2, inverse of the drag between 1 and 3, and inverse of the drag between 2 and 3. D21 equals D12 as a result of the Onsager reciprocal relations. In setting up these equations, we ignore three-body collisions. That is the assumption normally made in the development of the kinetic theory of gases. The Maxwell-Stefan diffusibilities, D12, D13, and D23, are all independent of composition for ideal gas mixtures. And these can be determined with very good accuracy using the kinetic gas theory. An important advantage of the use of the Maxwell-Stefan formulation, say in comparison with the Onsager formulation, is that the diffusibilities D12, D13, and D23 are independent of the choice of the reference frame because these diffusibilities are defined in terms of differences in the diffusion velocities, one with respect to 2, one with respect to 3, and 2 with respect to 3. The constraint imposed by the second law of thermodynamics demands that these Maxwell-Stefan diffusibilities be positive definite. The Maxwell-Stefan equations for the ternary gas mixture can be rewritten in this form using two-dimensional matrix notation. The column matrix J1, J2 represent the diffusion fluxes, and the column matrix of mole fraction gradients are indicated here. The constant of proportionality is the matrix of Fick diffusivities, and the elements of this matrix can be determined explicitly in terms of the three Maxwell-Stefan diffusibilities D12, D13, and D23 that are calculable from the kinetic gas theory. Note in general that since these diffusibilities are not equal to one another, the cross coefficients D12 and D21 are generally non-zero. The sign of these cross coefficients depends on how we number the species 1, 2, and 3. With a different numbering scheme, the signs of these cross coefficients may change. Let us present the calculations for the matrix of Fick diffusibilities for a ternary mixture of hydrogen, which is component 1, nitrogen, which is component 2, and carbon dioxide, which is component 3. The D matrix is calculated at the composition x1 0.25, x2 0.5, x3 0.25, and from the kinetic gas theory, the Maxwell-Stefan diffusibilities D12, D13, and D23 can be calculated, and the values are shown here. For the pairs D12 and D13, these are the hydrogen-nitrogen pair and the hydrogen-CO2 pair. The diffusibilities are significantly higher than the diffusivity of the 2,3 pair, which is the nitrogen-CO2 pair. The Fick diffusivity matrix has a large and negative value for the cross coefficient shown here, minus 3.83, which is larger than the diagonal element D22, which has a value of 2.16. This implies the following. If we did a set of experiments in which the gradient of component 2, that is nitrogen, is 0, we will note from this matrix equation that the flux of component 2 is equals minus 1 divided by Vm times D21 times the mole fraction gradient of 1. It is not 0, even though there is no contribution of the term containing the mole fraction gradient of component 2. Therefore, uphill diffusion will be experienced for nitrogen in experiments in which we maintain the gradient of the mole fraction of component 2 as 0. Duncan and Tour in 1962 published a set of diffusion experiments conducted in a 2-bulb diffusion apparatus connected by a 2 mm capillary tube. The initial compositions in bulb A and bulb B are indicated here. Interesting to note is that the nitrogen mole fraction initially is 0.5 in both bulbs, and therefore there is no driving force in terms of mole fractions for nitrogen. At time t is 0, the stopcock connecting the two bulbs is opened and interdiffusion is allowed to take place. The equilibration trajectories for hydrogen and carbon dioxide in bulbs A and bulb B follow the classical exponential increase and decrease that is to be expected as the bulb compositions approach equilibrium. The continuous lines shown here and the dashed lines shown here are the solutions to the Maxwell-Stefan equations using the data on the Maxwell-Stefan diffusibilities determined from the kinetic gas theory. The equilibration trajectories for nitrogen in bulb A are indicated by the red circles, and in experimental data for equilibration in bulb B are indicated by the open circles. It is interesting to note that despite the fact that the initial compositions of nitrogen in the two bulbs A and B are the same initially, the fluxes of nitrogen in bulb A and bulb B are non-zero, and this causes the approach to equilibrium in bulb A to exhibit a minimum, and in bulb B to exhibit a maximum before eventually they equilibrate to the same compositions in the time interval between 0 and 6 hours. We experience the phenomena of uphill diffusion for nitrogen. And what is notable is that the bulb B has a higher mole fraction of nitrogen, but this continues to increase at the expense of composition of nitrogen in bulb A. In other words, nitrogen is being pumped from bulb A to bulb B, and the reason for this in physical terms can be appreciated if we note that carbon dioxide in bulb A is initially 0.5 and in bulb B it is initially 0. The drag between nitrogen and carbon dioxide, which is 1 divided by the Maxwell-Stefan diffusivity D23, is large, and therefore the friction between nitrogen and carbon dioxide has the effect of dragging nitrogen from bulb A to bulb B. At this time, we note a plateau in the compositions. So even though there is a large difference in the mole fractions in the two bulbs, the flux of nitrogen at this point is 0 because the concentration profiles show a maximum here. And beyond that point, normal behavior manifests, and the two compositions in bulb A and bulb B approach one another to finally reach equilibrium at very long times. The continuous red lines and the dashed red lines represent the solutions to the Maxwell-Stefan equation using the data on the Maxwell-Stefan diffusivities determined from the kinetic gas theory. Indeed, in this paper cited here, Stefan anticipated the occurrence of uphill diffusion in ternary gas mixtures using a formulation that is almost identical to the ones we use to solve and obtain these calculated profiles. The experimental data of Duncan and Tour measured in the two-bulb diffusion apparatus is plotted in ternary composition space in the red circles denote the equilibration from the initial compositions to the final equilibrated composition. The green squares show the plots of the experimental data in bulb B as it progresses from the initial state to the final equilibration state. The continuous green and red lines represent the solutions to the Maxwell-Stefan equations, if the diffusion process is assumed to be uncoupled, in other words, the flux of each component is taken to be proportional to the mole fraction gradient of that component with a proportionality constant di that is independent of composition, then the equilibration trajectory would follow a straight line drawn by the dashed black lines. The serpentine equilibration trajectory is a signature for uphill diffusion and will be observed in several examples that will follow the slide. We ask ourselves the question whether the interdiffusion of the ternary gas mixture in the two bulb diffusion experiments of Duncan and Tour violates the second law of thermodynamics because of the uphill transport of nitrogen. The second law of thermodynamics mandates that the rate of entropy production be positive definite. The entropy production for the ternary mixture is given by this expression, where J1, J2, and J3 are the diffusion fluxes of hydrogen, nitrogen, and carbon dioxide, and these represent the gradients of ln x1, ln x2, and ln x3, where x1, x2, and x3 are the mole fractions. For uphill diffusion of nitrogen, this contribution of this term is negative. In other words, nitrogen consumes entropy. This is not disallowed because hydrogen and CO2 produce entropy at such a rate that the overall rate of entropy production is positive definite. Heliox therapy is applied to patients who have severe breathing difficulties. In that case, the patient is connected to a heliox cylinder, and typically a heliox cylinder has the composition 80% helium, 20% oxygen. Let's assume that the lungs of the patient is a 80-20 mixture of nitrogen and oxygen. Note that the oxygen mole fractions in the cylinder and within the lungs of the patient is precisely the same, that is 0.2 mole fraction. There's no driving force for transfer of oxygen, but due to the coupled diffusion effects, we have uphill transport of oxygen, and the trajectory followed by the compositions in the cylinder and in the patient are plotted here, and the trajectory that's calculated using the Maxwell-Stefan equations show a serpentine character. The Maxwell-Stefan diffusion equations for non-ideal ternary mixtures can be written in the usual manner. For species 1, for example, the force acting per mole of species 1 is balanced by the friction it experiences with species 2 and with species 3. And similarly for the force acting on species 2. The Onsager reciprocal relations demand the symmetry that D12 equals D21. So there are 3 independent Maxwell-Stefan diffusibilities, and these are composition dependent. We will see later that these can be estimated from the tracer diffusivity data. The second law requirement demands that the Maxwell-Stefan diffusibilities be positive definite. An important advantage of the Maxwell-Stefan formulation as opposed to the Onsager formulation is that the Maxwell-Stefan diffusibilities Dij do not depend on the choice of the reference velocity frame. These equations can be recast into the Fickian form by using two-dimensional matrix notation. The column matrix of diffusion fluxes is related to the column matrix of mole fraction gradients, the constant of proportionality being a square matrix of Fick diffusibilities. The expression for the matrix of Fick's diffusibilities can be derived, and this consists of a product of two matrices. The first one contains only the Maxwell-Stefan diffusibilities, and this matrix is multiplied by another square matrix containing the thermodynamic correction factors gamma 11, gamma 12, gamma 21, and gamma 22. The thermodynamic correction factors can be estimated from available data on thermodynamic phase equilibrium, say using the NRTL equation or the Flory-Huggins equations for polymeric systems, CalFAD for metallic alloys. Let's gain some understanding on the behavior of diffusibilities in the non-ideal ternary mixture of glycerol, acetone, and water. This system has a region in which we have phase separation. The green line represents the binodal curve, and the red line denotes the spinodal curve. Along the spinodal curve, the determinant of the matrix of thermodynamic correction factors is 0, and consequently the determinant of the Fick diffusivity matrix is also 0. Let's look at the elements of the matrix of Fick diffusivities as we move along this line from composition A to composition B to composition C to composition D. For composition A, the elements of the matrix of Fick diffusivities has these elements, and if we take the product of the cross coefficients and divide by the product of the diagonal elements, the ratio is found to be 0.01725. This ratio increases as we approach the region of phase immiscibility. And consequently, the magnitude of the coupling effects increases as we approach compositions close to phase separation. This has severe consequences for composition trajectories in regions close to the two-phase region. The entire set of experimental data of Grossman for the elements of the Fick diffusivity matrix in the homogeneous phase regions of the ternary mixture glycerol, acetone, water are replotted in this diagram. The y-axis represents the relative coupling effects of the D matrix, and this is expressed as the product of the cross coefficients divided by the product of the diagonal elements. The x-axis represents the relative coupling effects in the thermodynamic correction factor matrix that is calculated using the NRTL model, and the relative coupling effects are described by the product of the off-diagonal elements divided by the product of the diagonal elements. We note that there is a good correlation between the relative coupling of the Fick diffusivity matrix with the relative coupling effects due to thermodynamic correction factors. We conclude that thermodynamic coupling is the major contributor to diffusional coupling in organic liquid mixtures. Also notable is the fact that these coupling effects increase and are maximum at the spinodal composition, which is plotted by the stars here. This expression for the elements of the matrix of Fick diffusivities as a product of two matrices can be used to estimate the elements of the Fick diffusivity from information on diffusivities in the corresponding binary mixtures of the pairs glycerol water, glycerol acetone, and acetone water. For example, experimental data on the Fick diffusivities for the system acetone water are shown by the red circles. By dividing the Fick diffusivities by the correction factor gamma, we obtain the Maxwell-Stefan diffusivities, and the Maxwell-Stefan diffusivities indicated by the green squares shows a predictable composition dependence, and these can be estimated, say, using a interpolation formula on the basis of the self-diffusivities at either end of the composition range. So similarly, D13 can be estimated from experimental data on diffusivities in the binary mixture 1 and 3 and from the binary mixture of 2 and 3. So this matrix can be estimated from the constituent binary pairs. The matrix of thermodynamic correction factors can be estimated from say the Uniquac or NRTL parameters for phase equilibrium, and this affords a straightforward procedure for estimation of the Fick diffusivities. Consider the experimental data reported in 1985 for interdiffusion in the system glycerol, water, and acetone. These experiments were conducted in a Lewis stirred cell. The bottom cell contains a mixture of glycerol and water at this composition. The top cell contains a mixture of acetone and water at this composition. and at time t equals 0, the stirrers are rotated and interdiffusion is allowed to take place. The experimental data showing the approach to equilibrium is shown by the open circles in either phase. If we join this point with the initial point here, the mixture composition ends up in the two-phase region and the phases will equilibrate to the compositions shown at the end of this tie line. So in the glycerol-rich phase, the equilibration trajectory is from x0 to xeq, and in the acetone-rich phase, the equilibration is along this line. Note that the trajectories are not linear, but curvilinear or serpentine. The blue lines show the model calculations using data on the Maxwell-Stefan diffusibilities and thermodynamic correction factors calculated from the NRTL parameters and information on the diffusibilities of the corresponding binary pairs: acetone water, water glycerol, and acetone glycerol. So the serpentine trajectories can be predicted from the data on thermodynamic non-idealities, along with data on the diffusibilities of the corresponding binary pairs. The message to be drawn here is that serpentine trajectories are the result of diffusional coupling effects that are engendered largely by thermodynamic coupling effects. Consider the experiments reported by Varshnaya and Cooper in 1972 for interdiffusion in ternary mixtures of the oxides of potassium, strontium, and silicon. Two slabs containing two different compositions of the ternary mixtures are brought in contact to each other, and the diffusion couple is raised to a temperature of 1071 Kelvin for 4.55 hours, after which the system is quenched and the compositions of the three components in the two slabs are determined. The green squares here show the compositions of potassium oxide, and the red circles represent the compositions of strontium oxide. It's interesting to note that the experimental data for the profile of strontium oxide shows a minimum and a maximum, and in this region we have the phenomena of uphill diffusion. When this set of experimental data is plotted in a ternary composition space, we see that the equilibration between the two compartments follows a serpentine trajectory. This trajectory, shown by the continuous red lines, are constructed using the matrix of Fick diffusivilities with elements shown here. So the description of the serpentine trajectory requires the cross coefficient D21 of the Fick matrix to be significantly larger than the diagonal element D22 and also opposite in sign. So this explains or rationalizes the uphill transport experienced for strontium oxide. Ouzo is an aniseed-based drink consisting of 45% ethanol, 55% water, and 0.1% transanisole. When ouzo is added to water, it turns cloudy. Let's have a look at this experiment. The phase diagram of ethanol, water, and transanisole is shown by the green line, where the y-axis is the mass fraction of water and the x-axis represents the mass fraction of transanisole. This point represents the composition of ouzo, and the addition of water apparently enters the metastable region indicated in yellow. If the composition trajectory were to follow a straight line, no entry into the metastable region would have been possible. The foray into the metastable region is a direct consequence of a equilibration trajectory that is serpentine in character, and we imply that this serpentine trajectory is a consequence of uphill diffusion. The Ouzo effect can be exploited to produce nanospheres, and this technique is highly efficient because no expenditure of energy is required, and the process of entry into metastable regions is spontaneous. Let's turn to diffusion inside porous media, and we wish to demonstrate the occurrence of uphill diffusion inside micropores. To begin with, let's look at the classification of pore sizes according to IUPAC. A micropore is defined as having pore dimensions smaller than 2 nanometers. For mesopores, the pore sizes are in the range of 2 nanometers to 50 nanometers, and macropores have dimensions larger than 50 nanometers. Here we plot the potential energy of interactions calculated using the Leonard-Jones formula for 3 guess molecules: hydrogen, shown in black, argon, shown in blue, and methane, shown in red. Very close to the wall, we have repulsive forces, and a little bit further away, the attraction forces become evident. The potential energy for each of these molecules shows a minimum at a certain position, and the depth of the well is larger for methane than for argon, and the potential energy well for argon is deeper than that for hydrogen, and this follows the hierarchy of adsorption strengths. At a distance of 1 nanometer from the wall, the potential energy of interaction is 0. This implies that within a micropore, a gas molecule remains within the force field that is exerted with the pore wall. A mesopore, on the other hand, also contains a core region where molecule-molecule collisions are important and molecule wall collisions are of no importance. In other words, for mesopores, we need to account for molecule-molecule collisions as well as molecule wall collisions. For a micropore, the diffusion process is dominated by interactions of the gas molecules with the pore wall, and there is no core region where molecule-molecule collisions are prevalent. Let us examine animations showing the motion of hydrogen molecules and methane molecules in a silica pore of 4 nanometer diameter. We observe molecule wall collisions and also molecule-molecule collisions. For methane, which is most strongly adsorbed, there is a higher concentration of methane molecules near the wall surface. The Maxwell-Stefan equations to describe diffusion in mesopores must include terms that describe molecule-molecule collisions and molecule wall collisions. The diffusivity D1W is Knudsen-like in character. Indeed, the Maxwell-Stefan diffusivity D1W for hydrogen corresponds very closely to the Knudsen diffusivity. For methane, the situation is somewhat different because the motion of methane molecules does not exactly follow the Knudsen formula, because the molecules on colliding with a wall have a tendency to jump to a neighboring site on the wall rather than get reflected into the bulk. This bias in the molecular hops along the wall does not follow the Knudsen prescription of diffuse reflectance of molecules. The Maxwell-Stefan formulation reduces to the dusty gas model for ideal gas mixtures and for Knudsen-like molecule wall collisions. But this Maxwell-Stefan expression has a more general character. We consider an example in which the exploitation of uphill diffusion offers a technological solution to a practical problem. In many natural gas resources in remote locations, the nitrogen content can range up to 20%. The presence of nitrogen in natural gas lowers its heating value, and therefore, for transportation purposes, the pipeline specifications for natural gas transportation demand that the nitrogen content be less than 3%. So we would like to be able to separate nitrogen from methane, say, the major component of natural gas, such that in the device purified methane can be obtained that meets the pipeline specifications. In remote locations, it is economical to use pressure swing adsorption technology, and the question arises, which adsorbent is suitable for producing purified methane? The adsorbent requires the selective uptake of nitrogen and rejection of methane. Most known absorbents are selective to methane because methane has a higher polarizability than nitrogen. Therefore, the technological solution that is used in industry is to rely on the concept of diffusion selectivity, wherein the adsorbent material relies on the selectivity offered by intracrystalline diffusion in microporous adsorbents rather than relying on thermodynamic equilibrium. Let us see how that plays out. Let's consider diffusion in LTA foray zeolite. LTA stands for Linde type A, and foray zeolite has 96 sodium cations per unit cell, and the location of these cations is indicated by the blue spheres. The structure of LTA consists of cages of 11 angstrom diameter that are separated from adjacent cages by windows that have dimensions that are approximately 4 angstroms in size. You note that the windows are partially blocked by the sodium cations. Let us see how methane hops from one cage to the adjacent cage through the windows. You note that the dimensions of the methane molecule are only slightly smaller than the window aperture. Let's look at nitrogen. Nitrogen is a pencil-like molecule with a smaller cross-sectional dimension than the diameter of a methane molecule. Nitrogen jumps lengthwise across the windows, and due to the smaller cross-sectional dimension, the diffusivity of nitrogen is about 25 times higher than the diffusivity of methane. This factor of 25 serves to overcome the adsorption selectivity that favors the selective uptake of methane. Let us see how the competition between diffusion and adsorption plays out in the experimental measurements. In a classic paper published in 1958, Habgood reported experimental data for transient uptake inside crystals of LTA4A zeolite. These crystals are in contact with a bulk vapor mixture, 50-50 mixture of nitrogen and methane. The component loadings of nitrogen are plotted here in red circles, and the methane uptake is plotted by the green squares. Most remarkably, we note that the uptake of nitrogen exhibits an overshoot in the component loading before it equilibrates to the final value of about 1.2 moles per kilogram. The uptake of methane, on the other hand, is monotonous. So if we wait for equilibrium to be reached, then the component loadings within LTA foray zeolite would be far richer in methane than nitrogen. However, on the other hand, if we examine the uptakes during the early transients in its approach to equilibration, the component loadings are strongly in favor of nitrogen that has the higher diffusivity. So we could devise a diffusion selective process that operates in a transient manner in which the cycle times are adjusted so that nitrogen is selectively taken up by the crystals and methane is rejected into the gas phase. Let's model the uptake experiments for nitrogen-methane mixtures in foray zeolite by use of the Maxwell-Stefan equations. The Maxwell-Stefan equations can be written in two-dimensional matrix notation as shown here, where the molar fluxes are related to the gradients in the molar loadings. The proportionality constants are reflected in these two square matrices. The first one is a matrix of Maxwell-Stefan diffusibilities, where D1W, the diffusivity of nitrogen, is about 25 times higher than D2W, the diffusivity of methane. The square matrix here is a matrix of thermodynamic correction factors that can be determined from mixture adsorption equilibrium. Using the set of data on unary isotherms and diffusivities provided by Habgood in his paper, we can use the Maxwell-Stefan equations in order to calculate the transient uptakes of nitrogen and methane, and these are shown in black. The nitrogen overshoot is properly captured by the Maxwell-Stefan model, and the Maxwell-Stefan model also shows the monotonous approach to equilibrium for methane. Also shown here in blue are simulations in which thermodynamic coupling effects are completely ignored, and this matrix is assumed to be the identity matrix. In this case, no overshoot in nitrogen uptake is observed. In other words, the attainment of supra-equilibrium loadings and uphill transport of nitrogen is ascribable to the contribution of the thermodynamic correction factors, and therefore the proper accounting of thermodynamic coupling effects is essential to the solution of the technological problem of nitrogen removal from natural gas. In important separation applications such as reverse osmosis, dialysis, electrodialysis, and ion exchange, additional driving forces due to pressure gradients and electrostatic potential gradients need to be considered. These additional terms are simply added to the left member of the Maxwell-Stefan equations that we have considered so far. For example, for species 1, the additional terms would be the partial molar volume times the pressure gradient term, and for ionic species, the charge number of the species 1 times the Faraday constant times the electrostatic potential gradient. The constraint of electroneutrality needs to be invoked in addition to the Gibbs-Duhem constraint. An important advantage of the Maxwell-Stefan formulation in comparison to the Onsager formulation is that the addition of extra driving forces has no influence on the values of the diffusivities D12, D13, and D1n. This is in sharp contrast to the Onsager formulation, where additional driving forces causes the values of the Onsager coefficients Lij to alter. Now let us consider in the subsequent slides examples of reverse osmosis, dialysis, and ion exchange, and see how the Maxwell-Stefan equations can help us to model transport phenomena, and in particular uphill transport. Let's examine the phenomenon of osmosis that was first elucidated by Wilhelm Ostwald. We take a vessel containing two compartments separated by a membrane. The membrane is a polyamide thin film of a pore size of 0.5 nanometer. The membrane allows only permeation of water, but not salt. The right compartment contains pure water, and the left compartment contains 2% salt and 98% water. Initially, there is a driving force for transport of water from the right compartment to the left compartment. Diffusion of water will take place from right to left till thermodynamic equilibrium is reached. And at thermodynamic equilibrium, we must have a balance of the isothermal isobaric gradient of the chemical potential of water and the contribution due to the pressure gradient. If we assume the solution to be ideal, the expression for thermodynamic equilibrium can be written in terms of the differences in the mole fractions of water and the pressure difference across the membrane of thickness delta. And at thermodynamic equilibrium, the pressure difference can be calculated, say, for ambient conditions for temperature and pressure to be 2.75 megapascals. This is the osmotic pressure. In reverse osmosis, we need to overcome the osmotic pressure in order to be able to transport water from the left compartment to the right compartment. The Maxwell-Stefan equations describing water transport across the reverse osmosis membrane is written here, in which the force acting on per mole of water consists of the chemical potential gradient at isothermal isobaric conditions plus the contribution of the pressure gradient is balanced by the friction water experiences with the membrane. dWm is the Maxwell-Stefan diffusivity for interactions between the water and the membrane. UW minus UM is the relative velocity at which water moves with respect to the membrane. The membrane velocity is 0. There are several applications of reverse osmosis in industrial practice, and I give here one example in which a street vendor is selling pani puri to a horde of customers in Mumbai, and the pani he uses to serve up his delicacies consists of RO water. Hemodialysis is a membrane separation process that is used for purifying the blood of a person whose kidneys are not functioning properly. Blood containing urea is withdrawn from the patient and passed through a membrane unit that consists of hollow cellulose fibers. The membrane itself is about 10 micrometers thick. On one side of the membrane we have blood containing urea, and on the other side of the membrane we have a rinsing solution that consists, say, of water. Urea is able to transfer across the membrane into the rinsing solution, and purified blood is returned to the patient. The transport across the membrane can be described by the Maxwell-Stefan equations as described in detail in this book. Let's have a look at the hemodialysis unit. This is an animation showing the operation of the membrane. The urea flows into the rinsing solution and is taken away. The rinsing solution usually contains water. If the patient is connected to the hemodialysis unit for an extended period of time, there will be some ingress of water from the rinsing solution into the bloodstream because of the large difference in compositions of water. This results in bloating of the patient. Further details are provided in this textbook. For dilute aqueous solutions, the activity coefficients of ionic species are all unity, and if we assume that ion-ion interactions are of negligible importance, the Maxwell-Stefan formulation reduces to a simplified form shown here, where XW is the mole fraction of water, and this is practically unity. These equations, when rewritten in terms of fluxes, are identical to the Nernst-Planck equations that are widely used in practice. Let us examine how diffusion in ionic solutions lead to the possibility of uphill transport. Yang and Pintaro report a set of experiments on ion transport across a cation exchange membrane that is made of naphthalene. The left compartment contains salt solutions containing sodium sulfate and cesium sulfate. The right compartment contains sulfuric acid. The molar concentration of sodium sulfate in the left compartment is the same as the molar concentration of sulfuric acid in the right compartment. The concentration of cesium sulfate is significantly lower than that of sodium sulfate. The cation exchange membrane prevents the intermembrane transport of the sulfate anions and only allows the cations of sodium, cesium, and hydrogen to be transported. The experimental data on the uptake of cesium and sodium ions in the right compartment are shown by the blue circles and green squares, and the red triangles show the uptake of hydrogen ions into the left compartment. Remarkably, we note that the cesium uptake into the right compartment exhibits an overshoot in its concentration as it equilibrates to its final steady state value. The transport of cesium uphill and the occurrence of transient overshoots are quantitatively described by the model that incorporates the Nernst-Planck equation for describing the ionic fluxes, and these are shown by the continuous lines in this diagram. The physical explanation of the uphill transport of cesium is as follows. Hydrogen ion has a very high diffusivity, about a factor 5 higher than that of say sodium and cesium, and it gets transported very quickly into the left compartment, creating a charge imbalance, and therefore to maintain electroneutrality, that enhances the transport of cesium across the membrane into the right compartment. And for a brief period of time, the concentrations in the right compartment are higher than the final equilibrated values. Yoshida and Kataoka report experiments for transient uptake of cations in a cation exchange particle DOWX50 WX10. The cation exchange particle consists of fixed negative charges, and negatively charged anions cannot enter the particle. In one set of experiments, the ion exchange particle is loaded with sodium ions, and the bulk solution surrounding the particle contains a mixture of nitric acid and zinc nitrate. The transient uptake of hydrogen and zinc into the particle and egress of sodium cations from the particle are monitored in the experiments. The uptake of the hydrogen ions are indicated by the red circles. The uptake of the zinc cations is indicated here by the blue triangles, and the egress of sodium cations is indicated by the green squares. We note that the experimental data show an overshoot in the ion fraction of H plus before it equilibrates to a value of 0.5. The continuous solid lines are the simulations of the transient uptake using the Nernst-Planck equation for describing the ionic fluxes. The explanation in simple physical terms for the overshoot of H plus is as follows. The ionic diffusivity of H plus is about 1 to 2 orders of magnitude higher than that of sodium and zinc inside the ion exchange particle. Consequently, the ingress of H plus into the particle occurs at a faster rate than the ingress of the zinc cations and the egress of the sodium cations. The fast ingress of the hydrogen ions into the particle causes a charge imbalance that has the effect of slowing down the ingress of the zinc cations and speeding up the egress of the sodium cations. The net result is an overshoot in H plus, and you will note that there is a concomitant rapid decline in the ion fractions of the sodium cations, shown in green. In a different set of experiments reported by Yoshida and Kataoka, the cation exchange particle is initially loaded with H plus and the zinc 2 plus cations, and the surrounding bulk liquid mixture is a solution of sodium nitrate. The transient development of the ion fractions of sodium, zinc, and hydrogen cations are shown here in using symbols. The continuous solid lines are the simulations of the transient uptake using the Nernst-Planck equation to describe the ionic fluxes. The egress of H plus is very quick, and this enhances the flux of sodium into the particle, while the egress of zinc cations is slowed down. No overshoots or undershoots are experienced In this case, the transient equilibration trajectories followed by the three cations in the two experiments shown in the previous two slides are plotted in ternary composition space in this figure. It is noteworthy that the trajectory followed here, shown in blue, when the ion exchange particle is initially loaded with sodium, is exhibiting an overshoot in H plus, whereas the reverse equilibration, in which the particle is initially loaded with a mixture of zinc 2 plus and H plus, follows a completely different path that is not symmetric with the blue path. In the red path, no overshoot or undershoot in H plus is recorded. This underscores the asymmetry that is inherently present in ternary ion exchange processes. This asymmetry is adequately captured by the Nernst-Planck equations. Here are the major takeaways from this presentation. Thermodynamic non-idealities are very strong near phase transition regions. Such non-idealities have a strong influence on the Fick diffusivities, and within spinodal regions, the Fick diffusivities are negative, leading to uphill diffusion. The Maxwell-Stefan formulation is the most convenient one to use. The Maxwell-Stefan diffusivities are independent of the reference velocity frame. This is an important advantage over the Onsager formulation, in which the Onsager coefficients Lij depend on the choice of the reference velocity frame. Uphill diffusion is often engendered due to strong thermodynamic coupling. The Maxwell-Stefan formulation can be intuitively extended to include additional driving forces such as pressure gradients and electrostatic potential gradients. The Maxwell-Stefan formulation can also be extended to include additional guest species in the system. The influence of pore walls for diffusion in micropores, mesopores, and macropores can be accounted for by treating the walls as a pseudospecies in the mixture. Indeed, the Maxwell-Stefan formulation reduces to the dusty gas model for ideal gas mixtures inside porous materials. The signatures of uphill diffusion are transient overshoots in approach to equilibration, and when the equilibration trajectories are plotted in composition space, they follow serpentine paths. Such serpentine equilibration trajectories may exhibit forays into metastable regions, leading to the Ouzo effect. Here is a list of references that provide further details on the modeling of uphill diffusion using the Maxwell-Stefan diffusion formulation.